We can continue the discussion on hybridization. Today we will discuss sp2 hybridization. So already we discussed the hybridization is the intermixing of atomic orbitals of almost similar energy to form new orbitals of same energy and same shape. When one s orbital and two p orbitals are undergoing hybridization, we can call the hybridization as sp2 hybridization. Here we will discuss two examples. First one is BCl3 and the second one is C2H4. BCl3 boron trichloride and C2H4 ethene. In ethene, the ground state electronic configuration of central boron atom is 1s2, 2s2, 2p1. In the excited state, one of the 2s electron is promoted to vacant 2p orbital, as it is shown here. Yeah, 1s2, 2s2, 2p1. So in an excited state, this electron is promoted to one of the 2p orbital and it will undergo hybridization and you will get three sp2 hybridized orbitals. There will be one unhybridized p orbital, but there is no electron in that unhybridized p orbital. Therefore, the hybridization is sp2. The shape of the molecule is triangular with bond angle 120 degree. Here you can see the overlapping of atomic orbitals. It is sp3 hybridized orbital. First one, second one, third one. It overlaps with the 2p orbital of chlorine to form a sigma bond. Here, 2p orbital of chlorine and sp2 hybridized orbital of boron, another sigma bond, the third sigma bond. So it is the structure of BCl3 schema hybridization, then geometry, triangular, bond angle 120 degree, and overlapping of 2p orbital of chlorine, 3p orbital of chlorine and sp2 hybridized orbital of boron to form sigma bonds. Now the next one is C2H4, ethene, C2H4. Ground state electron configuration 1s2, 2s2, 2p, 2. The excited state, one of the electron from 2s will be promoted to 2p. Then 1s and 2p orbitals will undergo hybridization to form sp2 hybridized orbitals. Here we can see the first carbon atom, the second carbon atom. This carbon atom has three sp2 hybridized orbitals. 1, 2, 3. This one also has three sp2 hybrid orbitals. 1, 2, 3. These two sp2 hybridized orbitals overlap linearly to form a sigma bond, carbon-carbon sigma bond. Here 1s orbital of hydrogen and sp2 hybrid orbital of carbon overlaps to form another sigma bond, CH sigma bond, CH sigma bond, CH sigma bond, CH sigma bond. Here the unhybridized p orbital contain an unpaired electron. So it also can take part in bond formation. So here by sidewise overlapping, lateral overlapping, there forms a pi bond. So carbon-carbon double bond. One is pi bond and the other one is sigma bond. Now the remaining, in case of PCl5, it has sp3d hybridization with the bond angle 90 and 120 degree. The structure is trigonal bipyramidal structure in the case of PCl5. You try to write the scheme of hybridization and try to explain the geometry on the basis of hybridization in the case of PCl5. Now the next one is SF6. a sub 6 sp3 d2 hybridization with octahedral structure. Octahedral structure. sp3 d2 hybridization with the octahedral structure. That one also you try to write the schema of hybridization and try to explain the geometry on the basis of the concept of hybridization. Now we can go to the next theory, molecular orbital theory, to explain the geometry of the molecules. Molecular orbital theory was developed by F. Hunt and R. S. Millikan in 1932. The features of this theory are, first you try to understand it. First one, the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbitals. So what is the important concept in molecular? The most important concept in molecular orbital theory is that in molecules there are molecular orbitals and electrons present in these molecular orbitals. We know the structure of the atom. In an atom, there are atomic orbitals and electrons are present in these atomic orbitals. Similarly, in molecules, there are molecular orbitals and electrons are present in these molecular orbitals. And the formation of the molecular orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. Comparable energy, atomic orbitals of comparable energy only can combine to form molecular orbitals. Similarly, atomic orbitals of proper orientation. For example, we know there are three p orbitals on the basis of the orientation, px, py, and pz. Two pz orbitals can combine to form a molecular orbital, but pz and px cannot combine to form molecular orbital. That is proper symmetry. An atomic orbital is monocentric, while a molecular orbital is polycentric. Atomic orbital is around the nucleus of an atom, so monocentric. But the molecular orbitals are around the nuclei of atoms of the molecule. Therefore, that is polycentric. We cannot say it is around a single nuclei. So it is polycentric. Now the number of molecular orbitals formed is equal to the number of combining atomic orbitals, as in the case of hybridization. The number of orbitals combining is equal to number of molecular orbitals produced. When two atomic orbitals combine, so you will get two molecular orbitals. One is known as bonding molecular orbital and the other one is known as anti-bonding molecular orbital. What is this bonding molecular orbital? Bonding molecular orbital has lower energy and hence greater stability than the corresponding molecular or anti-bonding molecular orbital. So out of bonding molecular orbital BMO and anti-bonding molecular orbital AMO, which is more stable, BMO is more stable. BMO, the energy is lower than AMO, anti-bonding molecular orbital. The electron probability distribution around a group of nuclei in a molecule is given by the molecular orbital. But it's an atomic orbital, the three-dimensional region around the nucleus where there is maximum probability to see an electron. Similarly, in molecules, the molecular orbitals are three-dimensional region around the nuclei of atoms of the molecule where there is maximum probability to see an electron. The molecular orbitals, like atomic orbitals, are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and Hund's rule. So all the laws which is applicable to write the electronic configuration of atoms is applicable to write the electronic configuration of molecules. So these are the important postulates. But if we simply say the postulates, you will not understand it properly. So we can go to the details. how the atomic orbitals combine. That is known as linear combination of atomic orbitals, LCAO, formation of molecular orbitals by the linear combination of atomic orbitals. Mathematically, the formation of molecular orbitals may be described by the linear combination of atomic orbitals that can take place by addition and subtraction of wave functions in individual atomic orbitals as shown below. Wave function of molecular orbital psi MO is equal to psi A, wave function of atomic orbital A, plus or minus psi B, wave function of atomic orbital B. That means two molecular orbitals will form. Bonding molecular orbital sigma is formed by the additive overlapping of atomic orbitals A and B. So sigma is equal to bonding molecular orbital psi A plus psi B. And antibonding molecular orbitals are formed by subtractive overlapping. Sigma star is equal to psi A minus psi B. The molecular orbital sigma formed by the addition of atomic orbitals is called the bonding molecular orbital, while the molecular orbital sigma star formed by the subtraction of atomic orbital is called anti-bonding molecular orbital. Already we mentioned it. We can see the formation. Here it represents the atomic orbital. It is the atomic orbital. It is the other atomic orbital. And when these two atomic orbitals combine, additive overlapping results in the formation of bonding molecular orbital. Subtractive overlapping results in the formation of anti-bonding molecular orbital. It is higher in energy, it is lower in energy. And here there are two electrons. It is the case of hydrogen. An electron filling according to above principle. First electrons will enter into orbitals of lower energy. It is orbital of lower energy, and here filling of electron will take place. So it will be vacant. It is the overlapping of atomic orbitals. Now, which are the various possibilities? One is atomic orbitals are combining. Additive overlapping, subtractive overlapping. Additive overlapping results in the formation of molecular orbital sigma 1s. Sigma 1s. 1s is the atomic orbital and molecular orbital sigma 1s. So we are using quantum numbers to represent the molecular orbitals also. Sigma 1s. Due to subtractive overlapping, sigma star 1s will form. Here you can see between the nuclear electron densities minimum in antibonding molecular orbital. So that is unstable. But here between the nuclear electron density is maximum. So bonding molecular orbital is highly stable. So here we can see sigma 1s, sigma star 1s. Similar the case of 2s. When 2s atomic orbitals combine, we will get sigma 2s and sigma star 2s. Now the next one, 2p orbitals, overlapping of 2p orbitals. 2p orbitals can overlap in two ways. There is sigma overlapping and pi overlapping. In the case of sigma overlapping, additive overlapping and subtractive overlapping are possible, and here it is additive overlapping. Here you can see between the nuclei, the electron density is high, so highly stable, lower energy state. And here subtractive overlapping between the nuclei. Between the nuclei, the electron density is minimum. That is unstable. So which are the orbitals formed? Sigma 2p and sigma star 2p sigma 2p and sigma star 2p Now sideways overlapping. Sideways overlapping also possible in two ways, that is additive and subtractive. In additive overlapping, you can see between the nuclei, the electron density is maximum, pi 2px. Subtractive overlapping, 2x orbitals are overlapping. Here you can see between the nuclei, electron density is negligible. Subtractive overlapping results in the formation of pi star 2px. So pi 2px, pi star 2px, similarly pi 2py, pi star 2py. We have a set of molecular orbitals. What is the increasing order of energy of various molecular orbitals? And when we study it in detail, we can see different order for different molecules. For oxygen and fluorine, the first one is the order. But for N2 and the molecules below N2, the second one is the order. Sigma 1s is the lowest energy, then sigma star 1s, sigma 2s, sigma star 2s, sigma 2p pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2px for oxygen and fluorine. But in the case of nitrogen, you see sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. After sigma star 2s, the next one is pi 2px. But in the case of oxygen, it is sigma 2p Here it is pi 2px, pi 2px, pi 2py, then comes sigma 2p and the remaining there is no change, pi star 2px, pi star 2py, sigma star 2px. So it is the increasing order of energy of atomic orbital. So we can see the various examples in the next class. I think it is enough today, and we can stop it here, write the assignment and submit. Okay.